Well, excuse me. Good morning, good afternoon, and good evening, everyone. Welcome back. So last time, namely Monday, you saw what happens if one tries to be too nice and to adapt a perfectly fine proof to a marginally more relevant context, instead of just basically using that proof and proving that two posets are equivalent. But anyway, so today we'll pick up from there, and we'll state and prove theorem 1782, which is important part of the proof that OCA implies all automorphisms of the Calkin algebra are inner. So let's move on. Oh yes, actually, before I forget, the second problem set is due today, and I'm going to post a new problem set probably on Monday. But also, I'll see, depending on how well, depending on what solutions to problem set look like, I may go over some of the solutions in class. Yeah, okay. So. First, we'll need some of the notation that we used before when we proved that continuum hypothesis implies that Calkin algebra has an outer automorphism. We'll need more than notation, but let's start with notation. So first, remember T is the unit circle, and T to the n is just an infinite sequence as well, elements unit circle, which we think of as a compact metric space. And here we define this bi-pseudometric delta. So for I and j, which are natural numbers, and for x and y in the circle, we look at this formula here: xi x of j conjugate minus yi yj conjugate. And if f is a non-empty subset of the natural numbers, we have this other function delta f, which is just supremum of all delta ij's for all possible choices of pairs in f between x and y. And so here is what we proved maybe 2 or 3 weeks ago, that if f is a non-empty set, ij are natural numbers, x, y, z are sequences in the circle, then we have several equalities. So number one looks very similar to definition, but it's slightly different. From it, it is easier to see that delta is pseudometric when you fix x and y and vary I and j. Sorry, when you fix I and j and vary x and y. And anyway, so here are facts that we did prove about the pseudometric. Let me just go quickly over that. This one is quite important. Number two, delta f of x and 1, by 1 I just mean constantly one sequence, it is equal to the diameter of the image of f under x. Okay, this one says it's pseudometric, and this one says it's pseudometric in different way. It's translation invariant. Now, if you looked up in the textbook, you probably noticed that lemma 1715 has a sixth entry that I just ignored because I didn't need it back then, but you'll need it right now. So here is the plan. That sixth item in lemma 1715 is on the next slide after I swipe my iPad, but I don't recommend reading it because I actually digested it and rehashed it and stated it in a more reasonable form, what I believe is a more reasonable form, on the next slide. So, I mean, on next slide after that one. So I'm just including this for completeness. So here is the original statement. Never mind what that is. Let's just go on. And here is what I'll be doing right now. Okay, first we have definition of delta. Once again, well, okay, so counting 3 and 4, it's the same as 1 and 2, just that I forgot to reset the counter. Okay, so first, you see, first statement, first lemma actually doesn't have, it does have. U is in L infinity of n. Sorry, I forgot about identification. So U is in L infinity of n, which is identified with T to n, right? And it's also identified to a subgroup of the unitary group of B of H, right? So the first part actually makes sense. Oh no, actually both parts make sense. Oh yeah, okay. Right. Actually, I didn't have to write this. Well, let me raise it. Okay, so if U is a unitary on H, then we have these 4 inequalities. I'll discuss them as improving them. Only one of them is non-elementary. 3 of them are just elementary. And I'll be proving one by one, leaving the non-elementary one for the end, so you can try to guess which one is that, just to get some suspense here. Okay, so first, what I mean here, distance from U to T dot 1. So what is T dot 1? Well, this is really the scalars. Maybe it is good to say it this way. T dot 1 is simply the center of the unitary group of B of H. Right? So distance from U to the center is less or equal from diameter of the spectrum of U, which is in turn less or equal than 2 times distance from U to the center. Okay, why is that so? So let's prove them one by one. I'd say this one is the yellow one. How do we prove this? Well, just choose any, fix any lambda in the spectrum of U, then diameter of spectrum of U, then for every eta in the spectrum of U, the distance from eta to lambda is less or equal than diameter of the spectrum of U. But also, if you look at the distance from U to T dot 1, it is at most distance from U to lambda dot 1. Right, so that's the first inequality. The second inequality, let's make it red. Well, it's pretty much the same thing, just basically, why do we have 2? Well, distance from okay, so again, well, with the same fixed lambda, with same lambda fixed here, for every eta in spectrum, well, distance is less or equal than diameter, and by triangle inequality, you get that it is less or equal, that diameter is less or equal than 2 times the distance, right? So it's triangle inequality. Okay, the next one, let's say it's green, it is this one here. Well, this is just a computation, although I personally hate it when somebody says this is just a computation and skips the computation and leaves me wonder what computation. Well, just fix. Okay, so first we have to fix epsilon greater than 0 because we are not necessarily in actually we are in compact context. But anyway, I'll say a word about that. Fix epsilon greater than 0 and fix lambda such that the distance from U to lambda times 1 is less or equal than distance from U to T times circle. Well, then what is, if I fix A such that norm of A is at most 1, then UA U star minus A is less or equal than Okay, it's let's do it this way. It is equal to UA minus AU, and it is less or equal than UA minus what was lambda minus lambda A plus lambda A minus AU, right? Here, the point, of course, is that lambda commutes with A, and the right-hand side is at most this distance from U to T dot 1 plus 2 epsilon, but epsilon was arbitrary, and there we go. So that leaves us with this inequality here. And this one I claim is non-trivial. It can actually, you see, so far what I said had nothing to do with B of H or anything special. This is really the one where we have to use something about the structure of the unitary group. Now, here is important fact. The unitary group, with respect to weak operator topology, okay, first actually, weak operator topology and strong operator topology coincide on the unitary group. That's a little exercise. Now, why is that important? Well, strong operator topology multiplication is continuous, so we have a topological group. On the other hand, by Banach-Alaoglu theorem, weak operator topology, okay, by Banach-Alaoglu theorem, and another fact, which is that B of H is the dual space of trace class operators, and that weak operator topology coincides with weak star topology on bounded subsets of B of H. What that means is, well, because unitary group is closed subset of the unit ball, it is compact. So unitary group is compact, and therefore we have Haar measure. So we can fix Haar measure on U. So let mu be the Haar measure on U of B of H, right? So it's a probability measure because this is compact, and it is Borel measure, and it's also invariant under multiplication. And now what we have is the following. So let epsilon be the supremum over all A of norm at most 1 of UA U star minus A. Now, what do we take? Well, we take phi to be the integral over the integral of W U W star d mu of W. So W ranges over the unitary group, and we are taking integral with respect to the Haar measure. Now, what do we have? Well, V belongs to unitary group. Second, what is the distance between V and U? Well, it is at most integral of the norm WU W star minus U d mu of W. But now what is this? Well, this is less or equal than epsilon. You may complain that I had U star, here I have W W star, but you just multiply. Basically, this is really the same as WU minus UW, right? So it's simply the norm of the commutator, and that's exactly what the other one is saying. So you see at most epsilon, right? So it's at most epsilon, and moreover, what is V? Well, you see, by the construction, V commutes with any W in the unitary group. Now, I should just say we are taking left invariant Haar measure. I'm not sure if I said that. So because this is left invariant Haar measure, we have this equality. So what this means is that V belongs to the center of the unitary group. Okay, but now we are in Hilbert space. What is the center? The scalars. Right? If you have a unitary whose spectrum is it has more than 1 point, it is not central. Right? So V belongs to T dot 1, and as we saw, V is exactly that point that we were looking for. All right, so we proved these 4 inequalities, and here is corollary that will. I'm still mystified why exactly this happens at random points in time. Okay, so here is corollary. If we take any 2 unitaries, W and V, then we have these 2 inequalities. So basically, you see, we have diameter of spectrum of V star W in the middle, and it is book-ended by what is this? Well, it's really, you just look at conjugation by W and conjugation by V, and look at the distance between those 2 operators in the operator norm. So we have diameter of the spectrum is at most 2 times that distance, and at least 1/2 that distance. So basically, for practical purposes, we can, if we just care about what converges to 0, they are interchangeable. Now, how do we prove this? Well, of course, first, let U be V star W, right? And we'll use lemma. Now, let's see, how do we use lemma? Well, to prove this inequality here, diameter, so this is diameter of spectrum of U, it is less or equal than 2 times distance from U to T times 1, and distance from U to T times 1 is less or equal than this supremum, which is exactly this. For the other inequality, this one here, this diameter is greater or equal than distance from U to the scalars, and that distance is, once you divide this by 1/2, greater or equal than this here, and so you get this. Okay. All right. Any questions? Okay. So back to some back to reminding you what we did recently. So remember here, E is an element of that set of partitions of natural numbers into finite intervals, and we said U E tilde V if and only if conjugation by U and conjugation by V agree on F of E. And F of E was that Banach subspace of the Calkin algebra of all operators, which can be decomposed into sum of 2 operators, which are, the matrix is included in those blocks. Second thing, we identify T to the n with U of L infinity, which is subgroup of U of B of H, as I just said a moment ago. And finally, we say, oh yes, not we say, so this was definition. 1 was definition, 3 is lemma. X and Y are equivalent if and only if lim sup as I goes to infinity of delta EI union EI plus 1 of XY converges to 0. Now to put this in context, we can roll back to this here. You see it's this diameter of the spectrum of unitary. It's really basically it converges to 0 if and only if the conjugation by that unitary pointwise in point norm topology, actually in uniform topology converges to the identity function. And that's exactly what we are after here. Okay, so here is a definition. We haven't seen this definition before, although it was implicit in what we are doing. So let's see what we are doing. A family F of pairs EX for E in part and X sequence of sequence in the unit circle is a coherent family of unitaries if the set of those E which are first coordinates of elements of F is less or equal star cofinal in part. So this is big enough. And moreover, the coherence part, U and V are E equivalent whenever we have EU and FV in F, and E is less or equal star than F. So in other words, what this says is that this coherent family has the property that whenever you have two pairs.
Sorry, Ilijas. Can I ask you a question? Do you have a special reason why you use letters U and V and X and Y?
No, actually, I wanted to apologize about no. So basically, think of U as the same as X and V as the same as Y. I was just writing different parts of this at different points in time, and on one hand, I wanted X was a complex number and U was a unitary. So no, there is no special reason. Yeah, I hope it is not too annoying, but if it is, let me know. Don't be shy. Any other questions? Okay. Yes.
What is meant by delta A union EI plus 1 XY equals 0? I forgot. Well, I'm a bit lost here.
You are not listening. So let's go back here. This guy.
But you have the definition just for elements in T to the N, while your unitaries may not be in.
Yeah, but unitaries are in L infinity. I hope I said that. If I didn't say that, I'll say that now. The X is in T to N. Okay, so it's X. I said U is equal to X.
Okay, but on the other hand, in part 1, you don't need the fact that they are in T to the N. In this item 1 of your slide, this definition makes sense for any unitaries.
It makes sense. That is correct. And this is actually a very good point. You see, it may seem that what I'm doing today is very specialized because it is definitely not the case that every automorphism of the Calkin algebra is of this form, that it is on these big subalgebras implemented by unitaries which sit smack in the middle in L infinity. However, what we are going to prove is that if you give me any automorphism of the Calkin algebra, and if you allow me to use OCA, then I can find unitarily conjugate automorphism. I can just conjugate automorphism by a single unitary and make sure that it is of this form.
Okay.
So yes, so definition is more general, but it's actually more general than we need it. So basically, this first part here, I mean, this is a reasonable definition. It makes perfect sense to talk about unitaries U and V, but we just don't need it. We only need unitaries which come from L infinity.
Okay.
Now, okay, I should say one more thing before I go on. What does it really mean for unitary to belong to L infinity? Well, it depends on your basis. And not even on basis, really, we are in the Calkin algebra. So once you mod out the compacts, you may ask, so what unitaries belong to some copy of L infinity, or rather to some copy of L infinity mod C0? And the answer is any. So there is a theorem that is credited to 4 people, Weil, von Neumann, Berg, and Sikonia, and Weil proved and von Neumann proved it for self-adjoints, but the extension to normal operators, which is non-trivial, was done by Berg and Sikonia, and basically what the theorem says is that if you have a normal operator in B of H, then there is a basis for H, an orthonormal basis, and there is a compact perturbation of your normal element that is diagonalized by that basis. And even if your element was unitary, you can make sure that it's unitary. So if you give me any unitary in the Calkin algebra of Fredholm index 0, right? So it's definitely necessary. You don't want a non-trivial Fredholm index. Then I can find you, or rather Berg can find you orthonormal basis, which and the lift of that unitary to B of H, which is diagonalized by that. So basically, this is essentially what I said before, that this is not a loss of generality. We can just look at these guys. Any other questions?
Can I ask you a question, Ilijas?
Of course.
So basically the idea of these coherent unitaries is that you have like a copy of part n, and you are doing these unitaries to be the automorphism induced by them to agree in a bigger and bigger subspace.
Exactly. Yes.
Okay, so that is like the intuition of this.
That is modulo one thing. It's not copy of the entire thing. It's just a cofinal subset, but that's enough. Okay. Basically, no. If you have a cofinal subset, you can just extend it for any. And actually, this is important. So thanks for pointing it out. You see, if you have some let's say G, which is perhaps not the first coordinate of anything in F, then you can find E such that G is less or equal star than E, and EX belongs to F, and you can just add GX to F. Mm-hmm. Right, because it is X that is inducing this automorphism on F. So I might have, instead of cofinal, just said it is all of E, but it will be just important to some extent for us to deal with cofinal, and it makes no difference. Any other questions? No. Okay. So this was the same thing. And here is lemma that we proved a couple of classes ago. Okay, we didn't introduce coherent families yet. We haven't introduced coherent families yet then, but in this terminology, lemma said basically what Daniel just said. Every coherent family of unitaries defines a unique automorphism phi, which I'm going to denote by phi sub f of the Calkin algebra, which has the property that restriction of phi to f of E agrees with conjugation by U for every pair EU in F. I have to apologize to Mattel and to everybody for switching between X and U all the time. I hope this is not too annoying. So anyways, so we prove this, and proof is nothing really. All that matters is that part is directed set, and that lemma that every operator can be decomposed somehow as a sum of two operators which belong to some f of E for a fast enough partition E. Okay, but we want to go in the other direction right now. And here is what we are going to prove right now. If OCAT holds, then the automorphism phi f, as defined here, is inner for every coherent family of unitaries F. So we say that such F is trivial. Now, in set theory, you often have statements like this, that applications of forcing axioms in particular, that you have some non-trivial family like this, and forcing axioms that trivialize it. To non-set theorists, this may also ring a bell. It looks like cohomology. So what we are really saying is that certain cohomology is trivial. This can be construed in terms of in those terms, but okay, that's just fancy language. It doesn't really matter. Let's just prove a theorem and see how that will go. Okay, so here we are. Let me. For some reason, I believe that it's nicer to have this single page scroll, but. Anyway, so proof that OC implies that every coherent family of unitaries F is trivial. So we fix F, and F is a coherent family of unitaries. Now we fix a natural number D. D stands for distance, and we define a partition of pairs of elements of F in two pieces. And remember, as usually, there is asymmetry here. LB0 is supposed to be open. We'll have to check that. Partition is defined by putting a pair of pairs, right? So elements of F are pairs, and we have a pair of those, pair EU, FV, to be in this open set if this condition that I denoted LD0 here holds. So there are M and N natural numbers, such that if I take this interval, right? So it's familiar, right? So we are taking always union of consecutive intervals from E, union of consecutive intervals from F, and intersect those. And then we have delta I of UV is greater than 2 to minus D. So let's try to look at the picture here. So if this is partition E, it goes on here. And here is partition F. So intervals are different. You know, we're not assuming anything about what they look like. So if you take, for example, these two, you can take these two here, and you know, I is actually going to be the union of those two intervals in E. If you take some other pair, like I don't know, like these two here, well, then again, it seems that F somehow dominates E in my case. But you can see basically this is measuring how far they are. Anyway, let's see why is this an open coloring. Let me know if you're annoyed by this. For some reason, I convinced myself that it's nicer to scroll from left to right than to have continuous scrolling. But if I'm completely off, I'm definitely, I would like to hear that. Anyway, so why is it open? Well, you see here, from my picture, if you, let's see if I still have unused colors. So let's say that I have fix EU and FV, which belong to LD0. And now belonging is satisfied by some pair IJ. So let's say that I and J are here. Well, what are basic open sets? In the part, no pun intended, I can fix any finite sequence of intervals. I just fix enough to make sure that I and J are frozen, that I know what is EM and what is EM plus 1. In the F side also, you know, I just make sure to freeze enough of that. So I can go find the basic open neighborhood of the pair EF, such so that I know exactly what these intervals are. And now for the second part, that this delta is greater than this, delta is a continuous function with respect to the compact metric topology on T. So I can just find small enough open neighborhoods around X restricted to whatever this is. Let's call this M. And is it X? Okay, it's U, sorry. U restricted to M and V restricted to M. Right, so these are just finite tuples in some finite power of the unit circle. So there is a basic open set so that for any pair in that basic open set at this very pair I and J, this is greater than 2 to minus D. Right, and it's important here that I have greater than and not greater or equal. With greater or equal, it wouldn't be open. All right, so this is an open partition. And here is the claim. All homogeneous subsets are countable. Now this time I think if I press here, yes, okay, I think I learned how to do this finally. All right, so this is important. Remember, OCA tells us that if all zero homogeneous sets are countable, then something interesting happens. So let's try to prove this. So assume otherwise. And fix some X subset of F. Now, I should be saying uncountable, But you see, if I have an uncountable set, then that uncountable set has a subset of cardinality LF1. I'm assuming axiom of choice, right? If you don't assume axiom of choice, that's a false statement, but we live in a world in which we have a choice. So fix X, cardinality LF1, which has the property that X squared is subset of LD0. So actually I first have to fix D and fix S so that this happens. All right. Now, all the work from the last class was exactly understanding what these sets look like. So look at the set of all E such that there exists an X, EX. Okay, maybe I should put this to avoid ambiguity so that you know which one is small x, which one is big X. So let's call this X0. We'll call it X0 later on. This set here has cardinality LF1. It is subset of part N. Cardinality is equal to LF1. Okay, sorry. Well, actually, it's okay. There is a silly thing here, but just in case there is somebody extremely picky here in the audience, I'll say that without loss of generality, it is X0 that has cardinality LF1. You know, theoretically, it could happen that X has size LF1. Oh no, it cannot. All right, so let me just basically to avoid wasting time on things, so that assume that for every E there exists at most one X such that EX belongs to F. Right? We can assume this. Because you know, that's for some stupid reason you could have uncountable set of, yeah, okay, right, that's actually you can. So I'll have to assume this. All right, so anyway, so we have X0, which has cardinality LF1, and now from what we proved before, we can find a single partition in part that bounds uncountable subset of X0. Right, so by the last class, there exists F in part such that the set of all in X0, and now even E is less or equal than F. And remember what this means is not for all but finitely many, but actually for all. Each pair of consecutive intervals of E is included in pair of consecutive intervals of F. This is uncountable. It has cardinality LF1. All right, sorry, just a second. All right. So we have F. Now, what happens? Well, look at the following. Oh, yes. So without loss of generality, there exists an X such that Fx belongs to F. Why is that so? Well, because F is cofinal. Right, the first coordinates of F are cofinal in part. So we actually have this unitary here. And we can use this unitary to uniformize what we have down there. So now, fix EY in okay, so I have kind of lousy notation. So fix EY such that E is in X0. And now what do we know? We know that EY, comma, Fx belongs to LD0. Now, what does that mean? It means that there exists an M and there exists an N such that delta EM union EM plus 1 intersected with Fn union F.
Sorry, Ilijas,
yes.
But why do you say that EY Fx belongs to LD0? Fx is out of X0.
Oh, not.
I mean, you have your homogeneous set, and now you are taking a couple such that the first component is above all the.
Oh, no, that's right. Yes. No, I cannot say it. So yes, thank you. So that's not what I wanted to say. That's not what I should have said. Thank you. So we just look at these, right? So we don't know that, but there is something else that we know. Thanks, Matteo. So you know what? I'll just open the window. So it's somehow I have this effect that the moment I start talking, until I'm quiet, everything is fine, and just when I start talking, just the temperature shoots up and I start saying nonsense. So let's see if opening window helps. Okay, let me know. Let me help here. So what do we know about this here? Well, remember, because E is below F, we have that X and Y agree on E. Okay, and what that means is that limit as m goes to infinity, delta EM union EM plus 1 of XY is equal to 0. Okay. So what do we have? So there exists some K of EY, so that for all M greater or equal than K, let's call it K, this delta EM union EM plus 1 of XY is less than, how small I do want it to be? Well, 2 minus D minus 1 will do. Okay, now without loss of generality, K is equal to K there is K which is equal to all of them for all E in X0. Right, because this is a countable set, it's uncountable set, so by pigeonhole principle, there is a single K which agrees, which works for all of them. And one more thing. So also, for all, there is actually more than that. So and L equals minimum of EK is the same for all E in X0, right? So maybe I should draw a picture here. So basically, here is this EK, and we don't know what happens after that, but up to this point, I mean, from this point on, we have that delta is small. Now, what happens up to this point? We have some finite number of coordinates, and again, we are in compact metric space. So again, by another refinement, we have an uncountable subset of compact metric space which has complete accumulation point. So we can make sure that the maximum of x of j minus actually let me without loss to generality for all ex and in prime x prime in this set, I think I called it x. We have that if I restrict x to L and if I restrict x prime to L, the distance between them, which is just the maximum distance, is less than 2 to minus d minus 1. Right. So if I look at distance up to this point, they're all going to be close to one another. Now, from this point on, what do I have is that they will all be close to this x. But what that means, but by triangle inequality, right? So for ex and e prime x prime, what do we have is that this delta em union em plus 1 union em prime union this intersection em prime plus 1 of x prime, it will be less than 2 minus d, right? Because I'm, what happens up to this point, actually distances are small. After this point, that they are all close to that fx. Or, oh wait, was it, this was ey, sorry, I started writing ex at some point. These should have all been y's. Sorry, nobody stopped me. Y here, and Y here, Y and Y, right? So the distance can be at most 2 to minus d, but that is a contradiction. All right, so the key point was here that we have this coherent family, and once this element bounds all of these, actually, maybe I didn't make this point sufficiently clear. Let me just go back to this. You see, this is E is less or equal than F. What this means is that this EM union EM plus 1 intersected with Fn union Fm plus 1 is really equal to EM union EM plus 1, right? Because you can choose n, so this is included. So really, you're having complete control on what happens at these intervals. And because of that, you have triangle inequality, so you arrive at contradiction. Right. So, okay, any questions? All right, so now let's look at 1. Now, OCA tells us that for every D, we can cover our F by countably many LD1 homogeneous sets. So let's take a look at LD1. It says that for all every pair Mn, if you look at this interval I, it satisfies delta I of UV is less or equal than 2 to minus D. Right, so this is the negation of the condition for, I mean, this is complement of LD0. And now here is this notation which I used before. So if you have X subset of F, X0 is this projection to part of X. And here's a claim that may look familiar. If X0 is less or equal to Tarkov final in part, and X is partitioned into countably many pieces, then for one of those pieces called y, this set y0 as defined here is less or equal to star cofinal in part A. Now, if you look at this lemma, you may say, oh yes, you proved that last time. Well, no, actually, I went over its proof, but I proved something slightly different. I was talking about unbounded. Here, we are talking about cofinal, but proof is identical. So you see, we have a cofinal subset. We partition it into countable many pieces. If none of them were cofinal, we could just choose element which is not bounded by anything in here, right? So it's slightly different wording. Before it was element which bounds.
Do you have trouble with the audio of Ilijas? I'm having trouble.
He appears to be frozen.
Yeah, I also cannot hear
he's back.
you.
He's back.
I am back. I have no idea what happened. My computer was just knocked out of the meeting. Is my okay? My iPad is there. I can see it, so I don't have to ask. Okay, so I think I know exactly the moment when I was interrupted. So OCAT implies that for every d, we can write x as a union of countable many pieces. Let's call them y and d, n in n, so that each one of those pieces, y and d squared, is LD1 homogeneous. Okay, now what claim tells us is that there is always one of these pieces that is cofinal, at least one of them is cofinal. So each time we partition, we can pick a cofinal set. And even slightly better than that, even if we go to a subset of X, I'm being slightly sloppy here. See, it's not X that is cofinal. It is really this X0 which is cofinal, right? X is a set of pairs, but only on the first coordinate we have ordering. So even if we have a subset of X, so that this, let's call it F, so that F sub 0 is cofinal, that subset is covered by countably many homogeneous pieces, and one of those will have property at its first set of its first coordinates is cofinal. What that means is the following. It means that we can choose a sequence of sets. So we choose first F1 subset of F, which is L11 homogeneous. Then we can choose F2 subset of F1, which is L21 homogeneous, which is also cofinal, and so on. So we have this decreasing sequence of sets. Each one of them is, the dth set is homogeneous for the dth partition. Note, by the way, I don't think I ever said this, but it's probably clear that LD1 is greater, includes L1D plus 1. It's clear from here, right? Because the only place where D appears is here. You just have more stringent requirements for what this delta function is allowed to be. So we have this sequence now. You know, if we are super lucky, intersection of these sets is non-empty, and then we just choose that unitary and it works. Of course, that's not going to happen, but this is good enough. So this is good enough to get us to the proof. Okay, so so what do we have? Well, you see, There was a lemma that we proved a couple of classes ago. It was about unbounded sets. We have here even cofinal sets, so it's even better than this. And it was saying that if you have an unbounded subset of part, then for any, actually it doesn't even matter, then there is an infinitely branching element in that unbounded set. Namely, there is a finite sequence of intervals E0 up to EK minus 1, which is an initial segment of many elements of your set. And moreover, if you look at the next intervals in those segments, they're getting longer and longer, and they can be arbitrarily long. Right, so this we get only from unboundedness. And let me, I think it is, right. So it's here. So it's lemma 979. So for every D, we can find, and even we can find infinitely many such cases. This is important. So K is this length of the sequence. Why infinitely many? Well, the lemma was saying even more. It was saying for any fixed sequence such that, remember, we are talking about everywhere unbounded subsets. So any sequence such that in that basic open set, our set is unbounded, we can find a further subsequence which has this property. So we have infinitely many of those. And for every m, there exists E such that maximum of EK is greater than m. All right. So what does that mean? So we can find a sequence I'm just thinking of a good letter. So let's say L of n for n in n, such that this is all I need really, such that union of all those intervals Ej such that there exists X, E, X belongs to, this would be F, I should call this LD. LD and minimum of EJ is equal to this LD, so that this union is the interval from LD to infinity. And so this is property number one. Property number two was that this sequence is increasing. LD is less than LD plus 1 for all D. So the first property is exactly what I just said, that we have these infinitely branching nodes, and it's even weaker than that. This is really all I need. Okay, so it's clear how we get it. Right? So the picture, I guess, is clear. We have here L of D, and we can find arbitrarily long intervals. So this is this EJ. For something in our set, we can make it as long as we want. All right, so now we can actually forget about our sets being uncountable for a moment. So fix just a sequence. I'll put indices in a superscript. EDN X, oopsie, sorry. This is too fine for me. XDN in FD for n in n, so that limit as n approaches to infinity, xdn in T to N exists. Why I can do this? Well, this is a compact metric space. Right, so I have an infinite sequence. It's definitely an infinite sequence because these intervals are finite, but they're getting longer and longer. And so I can find this. Oh yes, that's one property. And second property is that this union. Okay, so I'm accumulating indices here. Union of these is exactly as it is there. So it's from L of D to infinity. Right, so I'm just choosing elements so that these intervals are getting longer and longer and longer. So I choose one sequence. Now that sequence is all around the place, but now I can go to a convergent subsequence. And this really means that at XDNs converge pointwise. All right, so let's call this something. Let's call this XD. Right, so XD is in T2N. Now, what do we have? Now, here is the fact. For every F, okay, for every D, and for every Fy in FD, for every J, such that, okay, actually I can, we have the following, delta of Fj union Fj plus 1, just in case intersect with this L of D infinity of Y, comma, what was the name, XD, is less or equal than 2 to minus D. Why is this so? Well, the analog of this holds for if I replace XD with any of these XDNs. Right, and you know these intervals are getting longer and longer. This is a closed partition, so because you're in closed set, this limit is less or equal than 2 to minus D. But now note, remember that at FD, that these partitions are not all around the place. That FD includes FD plus 1, includes FD plus 2, and so on. So what this means is that therefore, for all D less than D prime, if I look at delta from L of D prime to infinity of XD to XD prime, this is less or equal than 2 to minus D, because they both belong to this bigger homogeneous set. Okay, so now we just need to somehow assemble unitary out of these pieces. And how do we assemble that unitary? Well, we have to see what this really means. Okay, so here is what this means. Let me just add one. Oops, am I in the right spot? Yes, add page. So what this means is the next fact. For every D, there exists some scalar, let's call it lambda D, in the unit circle, with the property that if I look at XD, and if I look at XD plus 1, and multiply XD plus 1 by lambda D, then if I look at uniform distance between these two, so let's write out what it means. I'm looking at xj minus this j and supremum, but uniform distance from certain point on, j is greater or equal than L of D plus 1. This is less or equal than 2 to minus D. Right, so remember, this metric being very small means that you can multiply one of them and actually make it very close to the other one. That's exactly what we are doing. So just a picture, maybe, you see this is what x1 looks like. Now x2, okay, maybe you should make it look slightly crazier. So x1 looks somewhat like this. Now x2 does some complete garbage here, but from some point on, it is almost parallel to what x1 does. But you need to multiply by a scalar to bring them to the same place. And then x3, again, there is more garbage in the beginning, but later on it looks very similar to what these two look like and so on, but similar and more precise. And now we can finally assemble our unitary. So define z in T to n. Okay, so first, z of j is arbitrary if j is less than L of 0, we just don't care. Just choose your favorite complex number on the unit circle, it works. No, it's completely irrelevant. Okay, so now if j belongs to interval between L of d and L of d plus 1, then what do we want? Well, we want z of j. We want to take xd, but we just have to be careful about these lambdas. We have product. I think it's yes. It's j less than d of lambda j's. Right. So we are just shifting them around, and we accumulated finitely many lambdas here. Now, what do we have?
xdj, you mean?
X, no, there is no
d.
No, xd is the limit. Xd is the limit. Unless you said something here.
But zj is a complex number.
Oh,
no?
the xdj. Thank you. Yes. I didn't understand what you meant. Yes, this is what you meant.
Yes.
Yeah. Thanks. Of course, right. Yeah. So we are right. So that actually does belong to T to n. All right. Now then, what do we have? Well, for every d, if you look at delta from L of d to infinity of z, and actually for every d less than d prime, let's be even more precise, d prime, this is less or equal than 2 minus d. Right. So z works for all of them. And now,
sorry,
at the
can I
end,
ask a question?
Yes, of course.
So in the definition of zj,
Yes.
Is the j on the right side?
Oh, j. Sorry. Yes. I know what you're going to say. I know what you're going to say. This is different. Yeah. That's what you meant, right?
Okay. Thanks. Yeah.
Yeah. Thank you, Pedro. Yes, of course. Right. So I'm no. There is a finite set of letters that I use all the time, and of course I run into this.
So the I also here you have to change. In I belongs to LD plus 1. You wrote J.
Oh, yeah. Thank you. And I'll make it purple. Yes. Thanks. Right. Yeah. Thanks.
Oh.
Yeah. I think now it's okay. Okay, so then for all these blah, blah, blah. And I forgot what I want. I wanted to write something that starts with CH, but I forgot what that word was, so I'll just erase this CH. What I wanted to say is that this claim, maybe claim doesn't start with CH, that Z implements phi f on all of on the entire Calkin algebra. Basically, that Z is the unitary that we're looking for. Z witnesses that this is an inner automorphism. So proof, well, what we need to prove is that Z implements our automorphism on any FE. Right, so just fix in part n. Now, because our set that we started the proof with is f, it was cofinal in part, so we also can choose, we can assume that ex belongs to f. Okay, now ex doesn't belong to any of the fd's, it is somewhere in f. All right, now also fix epsilon greater than 0 and fix d, which is such that 2 to minus d is less than epsilon. D is big enough. And now fix fy such that fy belongs to fd and yeah, I think I learned how to do this. E is less or equal star than f. That we can do that. Now, what this means is that y implements phi f on fe, right? That is because x and y were E equivalent. All right. So, but also, what do we have is that delta from L of d to infinity between the unitary that we constructed there, z, and y, this is less or equal than 2 to minus d. Right? Now, what that means is, and finally I'm using those lemmas for the beginning, right? All that was just for the punchline. What this means is that AD y and AD, oh, sorry, Tony. This was way too much. This was way too much. It's not this. It's not. Sorry, I got carried away. So what do we have? Because Fy belongs to Fd, for every m, the following is true. Delta of Fm union Fm plus 1 intersected with LD infinity of z and y, this is less or equal than 2 to minus d. Right, so all that I know is that on the intervals which are controlled by f, from this point L of d on, this is less or equal than 2 to minus d. But now what this means is the conjugation by y and conjugation by z are, this difference is bounded by 2 to minus d plus 1 for all a in f of e of norm at most 1. Right, so this comes from those lemmas. So, so we didn't prove that Z implements automorphism on the nose, but we implemented it that we proved that it implements it up to 2 epsilon for any epsilon given in advance. Epsilon was arbitrary, and therefore this indeed implements the automorphism. Okay. So, so this ends this coherent family part of the proof. And I have a few more minutes, so I'll just like to make a few more remarks, but of course, if you have any questions, let me know. I should say that I hopefully will have more time, but this lemma was generalized by Andrea Vaccaro and by Alessandro Vignati in very different directions. This uniformization trick works in much larger context. And as I said, this is connected to set theory and cohomology and trivialization of cohomology under forcing axioms and things like that. But all right, so let's go back essentially to the part of the proof that we skipped. That is much more technical. Not trying to scare you, but I'll go slowly and just see what happens here. So I'll look at slightly more general situation, not just at the Calkin algebra, but at two coronas, Q of A, Q of B. I'm not even assuming that A and B are separable or sigma unit or even Cist algebras. I mean, this is completely general nonsense. So you have star homomorphism between two quotient structures. So here they are, right? So QB is M of B minus B. QA is M of A minus A. Here we have quotient maps. Here we have your star homomorphism. Even this is doesn't have to be isomorphism. Now, axiom of choice tells you that you can define a map phi star, which is a selection, which has the property that phi star of A has the property that its equivalence class is what? It is phi of the equivalence class of A. This is what I call a lifting of a star homomorphism. I should say that it is unfortunate terminology. Some people would prefer representation, which is also unfortunate terminology. In certain subjects, lifting means that it's actually a star homomorphism itself. I'm not assuming it. I just have a set theoretic map here, which satisfies this, and diagram commutes, and this is not a morphism. So this is important. Of course, if you had morphism to start with, it would be done. That's all the work goes into getting that. Another sub-definition, if diagram commutes only on some subset of the multiplier algebra, so X is here, then phi star is lifting on X. And sometimes, instead of thinking of X upstairs, in the multiplier algebra, we look at P of X, which is inside the Calkin algebra, and talk about phi as lifting on P of X. One particular situation in which, two important situations in which we look at liftings on X. Number one, you see, if you have a lifting on the unit ball, you know everything. Because Cist algebras are homogeneous, right? So behavior on any bounded ball is completely homothetic, if you want, to what happens on the unit ball. And second, one case that we'll be looking at a lot is the case when X is f of E, right? So we'll be trying to find liftings on Banach subspaces of this form. Okay. So here is definition. This definition requires a lot of justification. So I'll have to defend it before anybody attacks it. So a star homomorphism between coronas, so separable Cist algebras, now I'm assuming separable, is said to be topologically trivial if its restriction to the unit ball has a lifting which is Borel measurable with respect to the strict topology. Now, the point here is that if you look at multiplier algebra, look at unit ball and multiplier algebra of a separable Cist algebra, the strict topology is metrizable, separable, and completely metrizable. So it is what is called a Polish space, and those are basically the nicest spaces that you can imagine. Now, why did I say that I have to defend this definition? Well, what we would really love to have is just a lifting which is conjugation by unitary. Well, you cannot always have that. If A and B are abelian, for example, even if A is just abelian, there are no inner automorphisms because corona is also abelian. So everything commutes with everything, and any inner automorphism is trivial. And yet you may have some interesting automorphisms which still deserve to be trivial for different reasons. I'll just leave you to think what is the right definition of trivial automorphism of corona of an abelian C-star algebra. Really, just think about topology. That's a hint. And in non-commutative case, also, funny things can happen. And this, I think of this as a working definition. Now, why do I think it's defensible? Well, you see, there is a statement, one important theorem in set theory called Schoenfield's Absoluteness theorem. So it's Schoenfield's Absoluteness. I don't want to state it, but if you count the it's all about counting quantifiers, really. If you count the quantifiers, if you write a Borel function between unit balls of multiple algebras or two separable C-star algebras, and say, to say that this function is a lifting of star isomorphism, you can say it in a certain form that Schoenfield's absoluteness theorem applies to. It tells you that as you move between transitive models of set theory which have the same Aleph 1, the truth of that statement doesn't change. So basically what this means is that if you can find a Borel measurable map from unit ball to unit ball, which in some model, assuming CH or OCA or whatever, acts as a lifting of an actual isomorphism, then that property does not depend on the axiom that you chose. I'm lying a little bit, but not much really. So it's really about transitive models containing all countable ordinals. So basically, in that sense, this definition says we don't really know what is the right definition, but this one is good enough for now. We hope to figure out one day what is the right definition, but for now, this one works. Right, so to make a long story short, if assuming some forcing axioms or whatever, you prove that your isomorphism has a topologically trivial lifting, then you reduced it, you basically, the rest, the remainder of the proof is not set theory. Proving, figuring out what it looks like, whether it exists, has nothing to do with set theory. Okay. So example, there is a separable abelian C-star algebra such that corona has a topologically trivial automorphism that cannot be lifted by a star homomorphism. Now you may say, well, okay, maybe the right thing to say is lifting by star homomorphism. No, it's not. This is a nice simple example, so I don't want, we have only a couple of minutes. And I'll just finish with this in the next lemma. So if A is separable and non-unit of C-star algebra, then its corona has at most C. So C is continuum, it's 2 to Aleph 0, topological trivial automorphisms. Why is that so? Well, there are exactly that many Borel sets. If you look at Borel sigma field, it has cardinality continuum on any Polish space. And this is how many Borel functions there are. So each function gives you at most one of those. So there is a bound on those. And why is that important? Well, before we proved, actually we didn't prove this, I just stated I proved something weaker, but if you have a separable stable means that A tensor compacts is isomorphic to A, on unital, then corona has topologically non-trivial automorphisms. Why is that so? Well, we proved that there are 2 to Aleph 1 such automorphisms, and 2 to Aleph 1 is greater than 2 to Aleph 0. Well, not in ZFC, but assuming that Aleph 1 is equal to 2 to Aleph 0, which we are assuming. Okay, I said this in a funny way. So really what I should have said is that 2 to Aleph 1 is greater than Aleph 1. Right, so basically what we proved before was that Calkin algebra has not just outer automorphisms, but even topologically non-trivial automorphisms. And all right, so I think I should stop here, right? I should stop here, and for the next class, we'll go back to continuous functional calculus and prove a few lemmas purely C algebraic, and then attack the proof that all automorphisms are inner. Any questions? Okay, so I'm varying. I mean, actually my chat window was closed, but nobody asked a question. So I don't know if absence of questions means that everything is super clear or that nothing is clear, but okay, I'll just take it that you are adults and you can ask me if you have questions. Anyway, okay, so it was good to see you. Be careful, take care, and I'll see you on Monday.